Yeah, so everybody, thank you for coming back from our break. As I said before we left, we have 2 more presentations about Mini Challenge 2, which was all about pattern of life analysis in our data set this year. So we heard Joe's talk before the break, and we're gonna kick off this session with an honorable mention talk from submission 1004 from the SAS group that had a really excellent submission that used some of the tools that they've been working on for a long time to sort of look at this data set and identify some really good detailed patterns of analysis, which is what we awarded them an honorable mention for. So with that, let's turn it over to the SAS video.
I'm Falco Schultz, Distinguished Software Developer at SAS Business Intelligence R&D Division, and we'll talk about how we approach the analysis and data visualization. The presentation covers the overall process the team went through, the tools used, and some of the data visualizations created, given our findings. Before we start, a brief overview of what SAS is all about. SAS provides a platform for data analysis and visualization. Tools are provided for both programmers and data scientists without programming experience. Think about drag and drop as well as automated analytics. SAS also provides tools to publish results either using a standard reporting engine or to support advanced visual storytelling via interactive online or offline reports. So why did we participate? As developer in the R&D division, we're constantly looking for ways to improve our products. Not only do we have an agile development standards including acceptance and unit testing, but we also request feedback from our users given real-life data and use case scenarios. Opportunities like VAS Challenge gives us a chance to test the SAS platform and potentially find issues or options to improve the overall user experience. The mission was to analyze demographics and relationships of a city in the United States with access to detailed characteristics of about 1,000 residents over a period of 1 year. While Challenge 1 focuses on the city demographics and social relationships of the residents, Challenge 2 considers the patterns of life throughout the city. The challenge was to describe the daily routines for some of the representative people, characterize the travel patterns, and analyze changes over time and season. The team restricted the tools to use to a single platform, SAS Vinyl. This scalable, flexible environment not only provides access to advanced programming, artificial intelligence, and machine learning capabilities, but also allows data scientists to explore and visualize and publish insights to any audience. The process is summarized by 3 major steps: data management, data exploration and visualization, as well as publishing the results. All data import and management tasks were performed in SAS Studio, while SAS Visual Analytics was used to explore and create data visualizations. The final submission form was based on SAS Visual Analytics SDK elements, providing interactive offline access to report content. SAS Studio provides access to various programming interfaces, allowing users not only to import data, but also to apply advanced programming techniques to massage and adjust data structures. Some of the data files provided exceeded 100 million observations, so compression techniques were used to reduce storages and improve process performance. We applied basic formatting steps, adjusted labels, and performed data quality checks. Especially at the beginning of the study, we detected some unusual values for attributes such as rental, expensive, or travel patterns. SAS code was written to enrich the data, for instance, to calculate the turnover by measuring job starts and end times. For easier analysis and reporting, the team also decided to pre-aggregate and join some of the data, for instance, by including attributes such as participant or employer information in the status log file.
I believe we did just one that was
The team was provided with a set of polygon datasets describing the overall city boundaries and building shapes. SAS Visual Analytics supports custom map background by utilizing Esri's ArcGIS map time services.
I think there's
Esri tools such as ArcGIS Pro were used to build and publish such themed map services. SAS Visual Analytics supports AI-driven automated explanation capabilities. This feature lets data scientists quickly get an understanding of the data structure, variable relationships, potential data quality issues, as well as to detect outliers. For instance, we use this capability to analyze spending, for example rental cost, across various categories for each participant. We then created geographical visualizations to show the distribution
Yeah, I
of
thought
home and
our
business
the video
locations,
was, I think,
combined with spending and other attributes, showing an interesting geographical districts, such as differences between the central and the northwest parts of the city. Analyzing social relationships using network graph visualizations quickly reveals how employers are distributed in the city and how different employee groups with different education status travel to their job locations. As part of analyzing a participant's daily pattern, we also investigated restaurant and pub visits. It shows that eating out is a common activity among our participants and that different groups visit different locations throughout the year. We also identified businesses in different districts, which do better than others. For instance, the Central Business District hosts two of the most successful pubs, covering a combined sales volume of $1.5 million, or about 20% of all sales. Utilizing Sasvaya's analytical clustering and time series support helps to understand historical trends. It shows the seasonal changes for businesses as well as things like popular days or times to visit a pub or restaurant. We also took into account some of the demographics characteristics of the participants. Geographical clustering, for instance, shows that the majority of the families with kids live in the outer regions of the city, whereas people with higher happiness score live closer to the city center. Advanced visualization techniques were used to animate data changes over time. For instance, to better understand the city's traffic patterns and bottlenecks, we animated the traffic volume using geographical heat maps. The example here shows the changes of our traffic density by hour of a day, and one can quickly see that the northern gateway to the city seems to be one of the common bottlenecks during peak hours. Network graphs and the geographical maps as shown in the right-hand visual helps to understand the routes or distances people have to travel. It quickly reveals that more than half of the population has to travel long distances to get to work, likely contributing to the travel bottlenecks during the peak hours. Finally, we also took individual participants and analyzed their daily patterns and geographical movements. Shown here is participant number 50 and how he travels through the city during a given day. One can observe travel routes, purposes for stops, and of course duration. We also created individual dashboards to show activities and transportation changes over time. Path analysis and related Sankey diagrams have also been used to understand patterns throughout the day. So what have we learned? A single platform such as Sasvaya makes the data management and visualization effort very straightforward. There's no cumbersome import or export or conversion required, as everything is hosted within the same environment. Sasvaya also allows on-demand scaling, which was important as some of the data sources are very large. We used a number of visualization techniques, but things like geographical maps and analytical clustering really help to understand the distribution. While SAS Analytics supports outlier detection, it can be enhanced, and we identified a number of potential improvements to make the user experience better. We also detected opportunities to improve the interactivity of our offline visuals, as well as a better data tip support, especially in some of our geospatial heat maps. This concludes our presentation. Thanks again for allowing us to participate, and we are looking forward to next year's Ask Challenge.
All right, can we switch to the Zoom, please? And I'll remind everybody quickly, if you have questions for the speakers, please use Slido to put them in, and we'll read them out loud so that we can have a good discussion here. So we've got Don and Stu on from SAS to help answer questions here. And I'll just start with one of my own. So first I want to say I really loved how detailed the analysis was. In particular, looking at sort of the pattern of life for individuals, and there's so many different dimensions of what's going on. And one of the questions I had was, in the platform that you have, did you find it difficult or easy to do things like find similar groups of people based on their patterns, rather than just kind of like picking on one attribute? Were there ways of getting a gist of whether, some individuals sort of followed similar patterns of life?
I'll start out and say that one of the powers of the platform and the tool we use, the SAS VIA system and SAS Visual Analytics, is the ability to explore as you go. And so it did help us as we were taking a look at data and doing some data prep. And I think, as everyone knows, data prep is where you spend so much of your time. We would use the platform to write some code, generate a table that would help us along the way, visualize it, explore, and iterate through that process. So that was one area that I found that was very helpful in looking at the patterns of life. And then just some of our built-in network analytics helped significantly with that process as well. Stu, anything you would like to add?
Yeah, I totally agree. A lot of it was, really exploring the data with a lot of the code that we had written, the network analysis tools within Visual Analytics, which is our main visualization tool, was very, very helpful. We were able to really get a clear picture of what people are similar, what people are doing. And we've got a couple of tools that are built in that can automatically help pull that information out in front of us. That was really, really helpful. One of them called Automated Explanation that can tell us, hey, all of these people tend to do very similar things, in these types of areas. So that was a very, very helpful tool. Yeah.
Excellent. So I've got one more question. I guess reflecting back on some of what we heard before the break in Joe's talk, he sort of commented that this year's VATS challenge is a little bit different, right? It's about these sort of more open-ended exploratory questions. And, I was wondering, do you guys share this opinion that, these kinds of challenges, as opposed to asking to provide very specific answers, does this add value to the research community, do you think, to try to explore? Does it add a little bit of fidelity to real-world problems to have them be more open-ended?
I'll start out and say I really loved the challenge this year. One of the things that really resonated with me, and I've been doing the challenges for about 2 or 3 years now, was that it did feel a little more exploratory in nature, which our tool, our visualization and exploration capabilities are things we've been working on for, at least on the product that I use and my team works on, for the last 10 or 12 years. And the ability to every year see how that tool helps has been great. And it provides ideas for us, both in terms of what we can do from a product to have a stronger contribution back to our product. But it does also make me feel excited. This challenge this year I got really excited about and was just having a lot of fun. And I do, back to your original question about it, being a little more open-ended, I prefer that as opposed to a singular answer, in that it does kind of help you think outside of the box and you don't necessarily get too into one train or way of thinking.
Great. Yeah. Thank you so much. We got to move on right now, but yeah, again, thanks to Stu and Don for answering those questions and for the presentation. So let's give a round of applause.
And thank you for the opportunity for being able to present and answer the questions. We really, really appreciate it, and the challenge as well.
No problem. Okay, so let's move on to, could we move back to the PowerPoint, please? So we've got one more talk on Mini Challenge 2 about our pattern of life analysis. And this one is by a team at Purdue for their submission 1012 on CLUS bridges, multi-level abstraction for travel records. And this was a really interesting paper. They won an honorable mention for effective visual encodings, and you'll see that they took this metaphor of building bridges that represent travel journals and some of the movement there, and really drilled down into that. So really excited to see this talk. And with that, we could play the pre-recorded video, please.
We introduced CLUS bridges, a visual analytics system to abstract, summarize, and present a large size of travel records, from general observations to local details. At the macro level, the system clustered travel records into groups and divided the entire city into multiple regions to summarize overall city life patterns. At the micro level, we highlight an individual's daily patterns with interesting details illustrated. Based on the map and travel times taken to all locations, we divided the city into 15 regions, labeling them from A1 to F4. The ancient Chinese bridge was an inspiration for our design. Cluster bridges use as bridge-like arcs to visualize the volume, speed, and direction of traffic from one node to another. Then, it clusters travel journal data to better identify life patterns for each individual. Major components of cluster bridges are the traffic of locations and regions, routines of clusters and individuals, and trends and metrics of traffic. The bridge-like arcs reflect two-way traffic patterns from one location to another, using the convention of right-hand traffic. The width of the arc indicates the volume of traffic from one node to another. The colors distinguish weekday traffic from weekend traffic. The arc's curvature and dashes indicate the speed, calculated by the Manhattan distance of two nodes divided by their average travel time. The straighter the arc, the faster the speed is. Cluster bridges clearly shows that the traffic patterns between regions vary with time. We can see that during the weekdays, traffic rush hours occur around 7 a.m. and 4 p.m. Traffic from A1 to C2 is smooth, but traffic from B1 to A1, C2 to B2, and C2 to D3 are generally slow. By selecting different destination types, we can see when and where people travel from each region. Typically, people travel to nearby pubs and restaurants on weekdays and travel to remote regions on weekends. By filtering building types, weekdays, hours, and months, the users can easily view traffic patterns between different buildings. We clustered travel logs into life routines and verified these clusters with a UMAP technique. For each life routine group, we provided detailed travel destinations and statistics about time and stay duration. For example, one routine cluster is from the workplace to the restaurant during lunchtime. Another cluster is a group of drinkers that go to pubs during weekday evenings and any time on weekends. Participants with similar life routines are then further classified into 7 groups. For example, one group could be regular workers that on weekdays go to work in the morning, eat lunch at nearby restaurants, go to pubs after work, and return home to rest. On weekends, they regularly go to pubs. We can observe patterns from every participant, including details of their travel locations, preferred pubs and restaurants, employers, and durations of stays at each location. These maps help cluster and partition into bigger regions. By filtering by building types and other criteria, we can visually measure the busyness of different locations. For example, we can roughly infer which area is the busiest based on point distribution. Let's look at participant 9's life patterns. On weekdays, he commutes between his apartment in sector F2 and his workplace in sector E3, and he always eats at the same restaurant. On weekends, he goes to eat at a different restaurant and usually visits at least one of his 5 favorite pubs. Participant 101 has a similar weekday routine as participant 9, but prefers to stay in his apartment and go out for occasional meals on the weekends. We can see many different lifestyles in the city. As the cursor moves along the navigation bar, various lifestyles show up. Through navigating cluster bridges, we can view life routines in their clusters, read an individual's life details, and understand city changes and trends.
All right. Let's thank our speaker. And could we go to the Zoom for some Q&A? And again, I'll remind everybody, please put in any questions into Slido that we can send to Yohan. All right, can you hear me? I see that you're muted right now.
Yeah, I can hear you.
If you're able to, could you put your video on?
Oh, you mean the share my screen?
What's it? Oh, this is fine. So let's see, while we're waiting for questions to come in,
Okay.
I've got one for you. So I really liked this bridge metaphor that you worked on, in particular, kind of the way that you're able to summarize a lot of information through that glyph. It does tend to lead to a lot of like ink on the screen, right? And so I wondered if you thought about this problem where you're drawing a lot over kind of quote unquote flyover regions where people might not be sort of going a lot, but are getting like covered by these bridge cliffs. And if you thought about ways of adding like filtering to kind of drill in to still being able to use this metaphor, but without running into that kind of problem. So were you worried about this at all? And maybe did you explore other design alternatives where this won out?
Yeah, actually, initially we have some different design idea, and so like we hope to mimic the real route path that based on the base map provided in the dataset. But later we decided to use this kind of bridge-like arc shape to approximate the Manhattan distance to express the route. So. And this design and plans earns the majority in our voting. So that is why we choose this design idea finally. Yeah.
Okay, we got another question that's very similar to what I just asked about data density and whether that was a concern for you. So maybe we'll skip over that one. Chris asks, the arcs encode a lot of information, and how did you decide what to include when sort of plotting attributes on those?
Yeah, thank you. That is actually a very good question. So when we're doing it indeed includes a lot of information like the jobs, the finance, and even the hunger or no hunger, the status. But we feel that this probably not be much helpful to our analysis. So in our the final the designs, we choose the source and the destinations and the times, like the start time and the end time, the duration, and like this kind of metrics in our embedding in our final designs. So these metrics are what we considering and focus on finally.
Great.
Thank you.
Maybe one more.
Sure.
There's another one. Okay, so we have one that says, at what point in your analysis did you find the Bridges approach to be the most helpful? So where did that really pay off when you were trying to answer the questions posed by the challenge?
Yeah, the cluster analysis, I think the most important thing is that it can help us to group the people with similar lab patterns and routines together. For example, we can have the same group of people who go to work every day early in the morning, like at 7 or 6 o'clock, and go back in the evening, and have another group of people who usually went to the pub at night. So that is different group of their lab routines, and I think these are pretty helpful for our analysis to identify the normalities and the commons between them, and so to answer the questions in the answer sheet of the mini challenge 2. Yep.
Great. Thank you very much. Let's thank our speaker again.
Thank you so much. Yeah.
And could we go back to the PowerPoint? We're a little bit ahead of schedule. That's fine. So we can move on a little bit early to talk about Challenge 3. And right, with Mini Challenge 2 or Challenge 2, we talked about pattern of life analysis, which had this really broad view of how people's lives might be changing throughout this city over time, how businesses might be changing. And now we're drilling in just on the kind of economic health portion of that. So what are the questions that we put to our team? There were kind of 3 big, again, kind of exploratory questions. And the first was that over the period of time covered by this data set, which businesses appear to be more prosperous and which ones appeared to be struggling? And we really left it to the teams to figure out from all of that data that Jordan showed earlier, what does it mean to be prosperous? We've got revenue, transactions, maybe number of visits from different customers. All of these things could be factored in there. The second question that we asked is, how does the financial health of the residents in the city change over time? Right, not just the businesses. And there's information about, living costs, how much money is spent on rent and wages. And so could you identify, for example, whether some people are doing better over time or worse? And then related to that, are there groups that appear to exhibit similar patterns? Maybe it's the case that some groups actually over time seem to be doing better while others are doing worse. And could you identify those kinds of divergences? And the final kind of big question in Challenge 3 is to describe the health of the various employers within the city limits. And this, at a glance sounds related to this idea of being prosperous or struggling, but we really want to get at the idea of, how are employment patterns changing and happening, right? Is there more turnover over time at certain businesses? Is there more stability? And do we notice any correlations with different areas of the city where there's more turnover or less, right? So we're kind of getting at that question. So for the remainder of this block, I think there are 2 presentations, and the first will be for an award winner for Challenge 3, and this goes to submission 1033 from Fudan University for their submission Economic Viz, Visual Analytics for Financial Health, Employment, and Similar Life Patterns Mining. And one of the things that the committee really loved about this submission was its strong support for visualization-derived insight. And what you'll see in this talk, I think, is that a lot of different visual encodings that are linked together were used that helped them answer these questions and sort of correlate their answers across different visual encodings. And we really thought they did an effective job there. So with that, we can play a pre-recorded presentation from Fudan.
In this talk, I am going to introduce a visual analytics system for solving VAST Challenge Mini Challenge 3. This work is completed by Ting Liu, Huiting Wang, Ziyu Lin, Yexiao Li, Shuexi Wang, Yu Wang, and Siming Chen. The authors are from Fudan University. I will present our work in 5 parts. First, I will give a brief introduction to the background of Mini Challenge 3. Then, I will explain the data processing part and the methods we use in this system. In the third part, I will describe each view of the system in detail. Then I will demonstrate 3 cases to show the usefulness of our system. Finally, I will summarize the main contributions of our work. Mini Challenge 3 provides 15 months of check-in, income and consumption data, and several demographic variables for 10-11 volunteers, requiring the participants to evaluate the financial health of the city. We subdivide the goal into 3 tasks, that is, display development of businesses over the period, characterize financial health of the residents and discover similar patterns, explore employment patterns and turnover. We define the keys to our solution as time series visualization, trend analysis, time series clustering, and high-dimensional data visualization. For the first one, we use calendar heatmap to display trends and patterns of time series at daily granularity, weekly granularity, monthly granularity, and within a week. Parallel coordinates is a common tool for high-dimensional data visualization. We utilize it to achieve the 4 targets for its customizable and brushable axes. Now we turn to the data processing part. In order to better meet our analysis needs, we have processed a series of data tables. The main raw data we use is attributes and journals. The attributes mainly includes cross-sectional data of different subjects. For example, participants.csv includes the age of the participants, their education level, whether they have children, etc. Buildings.csv includes information about the location and type of buildings. The journals is panel data, recording data of 10-11 volunteers for 15 months. Financialjournal.csv records the income and expenditure information of volunteers' bank cards, and traveljournal.csv records the starting and ending time and spending of volunteers at each location. Checkinjournal.csv records each location that the volunteers passed through. By table joins and aggregation at different granularities, we obtained building locations, employment relations, and a series of economic time series. Taking employment relations as an example, we merged employers.csv, participants.csv, and traveljournal.csv, and obtained a series of valid indicators for each company, such as average hours worked, working hours, average salary, and job vacancy rate after some operations. The city has 4 economic entities, including 10 pubs, 20 restaurants, 880 participants, and 253 employers. Notably, 131 volunteers don't have any records after March 5, 2022, and therefore are excluded from the analysis. For each entity, despite the attributes we can obtain directly through raw data, we compute some additional attributes. For example, we calculate the revenue and traffic of pubs and restaurants through participants' travel journal. We add up food, recreation, education, and rent as cost, and divide by wage as cost-wage ratio. For employers, we can calculate the proportion of employees with kids proportion, the average age of employees, age mean, the number of departing employees, and so on. Then we introduce the methods we used in our system. We can classify the data into time series data and non-time series data. Time series data include wage, food, recreation, shelter, cost, etc., while non-time series data include age and education level of participants, number of employees of employers, etc. For different data and different targets, we apply different algorithms. To explore the trend in time series, we use lasso regression. To explore similar patterns in time series, we use DBS-CAN clustering. To perform clustering in non-time series attributes, we use k-means. We further illustrate how we use DBS-CAN for time series clustering. We use the correlation coefficient as a similarity measure between 2 time series. For example, for the above graph, the correlation coefficient between the 2 time series is 1, and for the below graph, the correlation coefficient is 0.29. Then we can define distance as 1 minus correlation coefficient. With this definition, we can see that the more similar the time series, the smaller the distance. DBS-CAN is a density-based clustering algorithm. Given a set of points in some space, it groups together points that are closely packed together, marking as outliers points that lie alone in low-density regions. For example, by applying DBS-CAN, we can classify the average wage pattern of weekdays into 21 categories. In this part, we will discuss our system design in detail. Our system is completed by Vue.js, D3.js, and Python. It contains a console and 4 views, that is, map view, bipartite view, calendar heatmap, and parallel coordinates view. The map is used to provide a spatial perception of the economic situation of the city. There are 2 modes, the default mode and the turnover mode. The 4 colors represent the 4 types of economic entities of the city. For example, the orange dots represent employers. In the default mode, the color shades encode the economic volume of the entities. For bars and restaurants, the economic volume is the total revenue of the whole period. For participants, the economic volume is the total wages received for 15 months. And for employers, The economic volume represents the total wages paid. In the turnover mode, the size of the circle encodes the number of employees who left the company. With these settings, we can see more intuitively the geographical distribution of employers. The bipartite view is used to show the employment relationship and reveal the turnover. The circles in the inner ring indicate employers and the circles in the outer ring indicate participants. The lines indicate the employment relationships. We use red lines to highlight those cases where there are multiple employment relationships on one person. When the mouse hovers over a particular dot, we can see the specific employment relationship. In this case, participant with ID 497 has worked for 2 companies, that is employer 397 and 848. The calendar heat map is used to show trends and patterns of an entity at daily granularity, weekly granularity, monthly granularity, and within a week. Users can select specific individuals and attributes that they want to explore. For participants, the available attributes include wage, food, education, cost-wage ratio, apartmented, etc. The first day of each month is highlighted with a black border to reveal the patterns of consumption on these days. Users can easily spot the pattern that both education and shelter occur at the beginning of the month. We can see the life pattern of each volunteer under different granularity of clustering with the help of calendar heatmap. The calendar heatmap can also be used to show the cyclicality of economic activity in other economies. For example, pubs are more profitable on Saturdays, and there is a peak in business at the end of the month, and restaurants have higher traffic from Monday to Friday than on Saturday and Sunday. The parallel coordinates view is the core view of the system. It is used to explore high-dimensional data, compare multiple time series, and display clustering results. We plot the non-time series attributes on the left and the time series attributes on the right. To utilize this view, for non-time series attributes, we provide the function of dimension-free combination E1 and color-coded attributes E2. For time series attributes, attribute switching E3 and time range filtering E5 are available, as well as 2 modes E4. The weekday mode and the month mode. The weekday mode takes the average value for each day of a week and is used to present the cyclical nature of city life. The month mode sums up each month and is used to present the long-term trends of economic variables. We can pick the variables we want to understand and choose different time series properties to observe the implied patterns. The console is closely linked to other views. Entity switching, A1 time trend analysis and similar pattern clustering, A2, can be performed. In trend analysis, users can choose the time interval, trend column, and parameter alpha for lasso regression. After clicking the Submit button, the backend will perform the regression and classify the results into 3 labels according to the coefficients: 1 for the upward trend, 0 for no trend, and -1 for the downward trend. The results will be updated in the parallel coordinates view. In similar pattern clustering, the user can perform k-means clustering for non-time series attributes or DBSCAN clustering for time series attributes. The console helps us to better explore the whole system. In this part, we demonstrate 3 cases to show how we get insights from the system. Through Map View, Bipartite View, and Calendar Heatmap, users can observe how people change their jobs in the city. From the map view, it can be seen that the areas in the city where departures occur more frequently are the central, A1, and the eastern, A2, while companies in the southern, A3, are more stable and there are no employee departures. The red line in B clearly shows all separations throughout the whole period. By hovering the mouse over the outer circles, you can see all the companies where the employees have worked. In this example, the employee with ID 40 has worked for companies 420, 862, and 1281. We can further verify this through the calendar heatmap. C. Set target ID to 40 and target attribute to employer ID. The three colors in the calendar heatmap suggest three different companies. The system is also useful to find similar life patterns. From the calendar heatmap, we can find that the resident's life is cyclical. For example, the participant with ID 840 does not work on Tuesdays and Wednesdays, B1, while it can be found that he spends more on food, B2, and recreation, B3, on these 2 days. Using DBSCAN clustering in the console, we can see that the system clusters 21 work patterns, C1, 15 food spending patterns, C2, and 9 recreation patterns, C3, respectively, with the pattern column set to wage, food, and recreation. The system is useful to explore high-dimensional correlations. We can find some interesting patterns by brushing on the non-temporal attributes. By selecting attributes of interest to plot, mapping color to specific attribute and brushing. In this case, we find that people with high recreation wage ratio have higher joviality, despite their relatively low wages. Map the color to wages sum. We find that people who make the most money have lower recreation wage ratio and joviality. Finally, in this section, we will discuss the most important contributions of our system. The main contribution of our system is to make full use of the feature that parallel coordinates can well represent the intrinsic connection between multiple variables, and to add a time axis on top of that, in order to better observe the temporal trend existing between variables. Different algorithm choices, such as k-means, DBSCAN, and lasso regression, are provided to facilitate users to explore the variable relationships according to their needs. In addition, the rich variable checkboxes are also a highlight. That's all. Thank you for listening. Here is the homepage of our laboratory. If you have any questions, do not hesitate to contact us.
All right, let's thank our speakers. And if we could switch over to the Zoom, that would be fantastic. So can you hear me, Ting? See that you're muted still?
Wait, yes.
Okay, great, I can hear you. So we actually have several questions that came in during the course of your talk, and I'm just gonna pick through these a little bit. So the first one is, how did you decide what kind of supplemental attributes to calculate that were useful for augmenting your data analysis? So where did you kind of create your own attributes that you derived from the raw data, and which of those turned out to be useful or less useful?
Well, that's a good question. We thought about whether we could exploit more attributes in order to analyze the data better. So we add some additional attributes. Most of the attributes of the employee are useful, such as paying wages, job vacancy rate, and they are useful because they can be combined with parallel coordinate viewed for analysis. And maybe I can't remember the details So maybe I should go for these questions later.
Okay.
Thank you.
Yeah, we can move on to a different question. So I'm going to combine a couple questions here that were around this question of using dbScan. So Iris asked, can you explain why you use dbScan to cluster the time series data? And then there was another question that said, why use dbScan on the time series data, but k-means on the non-temporal data? And just explain the choice of that a little.
Well, okay. That's a good question. Thank you for asking me that. Actually, we first used k-means to cluster time series where the results did not meet our expectations. We think that it is because k-means doesn't consider the sequential nature of the time series when clustering. So it reminds us to use correlation coefficient to measure the similarity of two time series. And we define the distance as 1 minus correlation coefficient. And we first applied hierarchical clustering, but it is hard to choose the number of clusters, and the results are hard to explain. And then we tried dbScan, and we find this algorithm is effective to cluster similar time series. So we apply it. That's why we use dbScan to cluster time series. As for the question that why we use k-means, we use k-means to cluster non-time series attributes. Well, let me see it.
Okay. Did you have more to say on that point?
Yes. First, k-means is a popular clustering algorithm, and it is easy to understand. That is why we use it to cluster non-time series attributes. I hope this can answer the question.
Thanks. So I think we have time probably for one more question. And this one's really general. So what is the most challenging and time-consuming part of the work that you put together here?
Well, let me see. That's a good question. The most challenging part, I think, is to find and display the patterns in multiple time series. It's a really difficult question, and there are many relevant studies. I think in this work we have made some progress, but it's not perfect. So I think the most challenging part in this work is it. Thank you.
All right, let's thank the speaker. And I will remind everybody that if you do have more questions, we do have a Discord channel. I don't think we've mentioned that today yet, where you can pose questions to the authors. And of course, feel free to reach out. I know we ended a little bit earlier. I still need.
Sorry. Don't take Jordan anywhere. I'm just killing time for you.
Okay, perfect. Okay, so we've had a series of virtual presentations today, and I'm really excited for the last talk where we have our in-person presenter, which is wonderful. So we have an honorable mention for Challenge 3 from a team at VRViz and Virginia Tech for their submission 1024 about comprehending city economics from heterogeneous data. And one of the things that the committee really wanted to recognize in this submission was sort of this focus on methodology and kind of connecting the dots between outlining metrics and how they're going to investigate those. So we really wanted to highlight this clear articulation of hypotheses and metrics. And with that, I will hand it over to our speaker. Do you need any of this? No.
HDMI. Yes. Okay. Thanks first for the organizers for this great vast challenge. As many people said already, it was really a challenge, and but fun at the same time. Thanks. Thanks also that we have the WIS live again in presence, partially at least. So it's nice to be here, and I hope, yeah, that we will continue just like this in future years. So I'm presenting this work, which we did together with my colleagues from VRWIS, and Krešimir Matković, Rainer and Thomas also from VRWIS, and Disha, Nikita, and Dennis are from Virginia Tech. So I will start for this with data and processing. As you have already heard many times today, there were a lot of data available in many files, and we needed them to convert them to data tables, basically. We used many F# and Python scripts. Thomas was in charge with F#, very efficient, and I was in charge mostly of Python things. So, but I was really impressed with F# efficiency. We are using in this challenge Convis. This is our coordinate multiple views tool developed at VRWIS, which supports complex attributes and like time series and other stuff, and in advanced brushing techniques. What I mean with complex attributes, we created two data sets. One is citizen-centric and one is business-centric data set. The citizen-centric data set is one item is one citizen, so it has different kind of attributes like participant ID, household size, and so on, as we heard today. But we have a special type of attribute, which is a time series attribute. So in one record of data, you can imagine like you have a table, and you have now many rows here for each participant, and you have this number, how old this person, and so on. But also you have a time series, for example, spending on education over time. And this is in one record. This is important later for brushing. And then we also have business-centric data, where one item is not a participant, but a business. So we have business ID. We can, again, categorical, numerical attributes, but we also have time series attributes. Time can be anything. I mean, it can be on a daily granularity. It can be weeks, months, hours, minutes, whatever. Or we can group it as we wish. So, as I said, Convis is our tool. It's a research prototype content multiple view system. We can configure views freely, and we have advanced brushing. And this is a standalone Windows application developed in C++, OpenGL, and Qt. So you can imagine when we develop a new view here, it's probably not so efficient as doing like modern JavaScript things where we are faster, but here we have, I would argue, maybe better performance on costs of longer developing time. So we developed the new map view using this technology. So we basically parsed the buildings, and then we made this drawing, as you see it many times. We can also here switch on and off these special buildings or special positions, like, okay, buildings themselves, so we can show the map with buildings or without, with apartments, schools, employers, pubs, and restaurants. And we can adjust size of the glyphs for each, colors, and so on. And we did something else. We allow to show additional statistics on the map itself. Here, for example, you see for each pub a histogram. And this histogram has 5 bins, and each of these bins, the leftmost bin is the number of visits where visitors traveled a short distance to the pub. So they just come nearby. The next bin is the visitors who traveled short to medium distance. Medium distance is the next, medium to long distance, and long distance. So we computed these distances, and then, of course, we can show these all histograms in a separate views. But we thought it's better to show them in the map itself, so that you have this spatial context much easier. You can see it where it is. And then you can see, I mean, this we saw today in the morning, who was looking at it, these 2 pubs that are doing particularly fine. This is this pub that also has customers that travel longer time to the pub, and this one that also has longer customers that travel longer to the pub. So it seems they are more popular because it's worth traveling there. We also have the histograms for the way back, because we thought maybe someone is working somewhere, so after the work goes to the pub, this is close distance maybe, but then travels home back. But the distribution is similar. So the popular pubs are the popular taking either way. This now looks very cluttered and like spaghetti code build image, but still this is our curve view. I told you about this curve attributes, time series attributes. So we show here all curves for all participants, all businesses at once. This is just one example here. And this is spending on recreation. So how much do they spend over time? And then you can see here we can also brush. So we can say, okay, we have a line brush. We just draw a line, and all curves that cross the line are selected. So we can see here a subset of people who here have no spending on recreation, but on some other times they do have, some more, some less. We can refine the brush, we can combine it with another line and see the details for the participant or business. We also use many other standard views that we have in the system, like histogram, scatter plot, parallel coordinates, and all views are coordinated. Now I will show you 3 brief examples on what we find out, which we find like interesting. The first one is called food, money, and joviality, or what makes you happy. So, spending on food. This is for 1,000 participants approximately, their food spending over this months. And you can see like that some people spend not so much on food. This is like negative spending because the amount is given as you spend, like your bank account is going less. So basically, these people never spend on food. These are those participants that left the experiment. These people spend not so much, these people spend more, and the lower part spends a lot on food. And we also have this curve. We saw aggregation of this graph in some of the previous talks. This is money balance over time. So as time goes, every participant has its own curve or hers, and this is the how you have more and more money. So as we saw this in this example, our people are living well. Everyone has more and more money. Of course, some of them have much more and more, and some not so much more and more. But in general, everyone is prospering. So, and this is now joviality. We had in dataset joviality index. For those who didn't know what joviality is, and I belong to this group, this is some kind of factor that shows how people are joyful or happy. This is how I interpreted it. So what we can do now, we can brush people who spend a lot of money. Interestingly, these people do not have a lot of money, but they still spend a lot on food, and they're happy. If we brush now with other brush in other color, just to compare, people who have a lot of money, they don't spend a lot on food, and consequently, maybe they're not so happy. So maybe this helps you answer the question, what makes you happy? So, is it having a lot of money or spending a lot on food? So, the next example I would like to show is this education fees, or can we map fees to schools? These are education spendings over time. Again, each participant has its own curve, but you can see here just a few curves, kind of, because they overlap. So some people do not spend anything on education, and we assume this education spending, this is school fees. So people with children pay the schools. And basically, you have here some people that pay not so much, and you see these regular costs. So they have to pay it regularly, and some have to pay this amount, some pay this amount, this amount, this amount. There are 4 amounts. If you would brush, for example, this curve that is 0, it remains 0 all the time. So we don't have people who don't pay school and then start paying school, or who stop paying school. We also don't have people that change the amount. So once lowest amount, all the time lowest amount. So there are no students that change the school. And so I don't know why I don't have it. So now, if we brush the least expensive school, then we can see the stars are the 4 schools, and the orange dots are places where people live who pay the cheapest school. So we assume that this school is the one with the lowest fee, because the people kind of live in the vicinity of this school. No one from here goes to this school. The next school, the second least expensive school is this one. No, it's not. We don't know this is our assumption, because this is orange dots show the positions of people where they live who pay this amount. And we assume that this is probably the school, because this is the school. They are clearly clustered around one school, so we assume this is this. And the next one, this is the one. Again, we have a clear cluster of the apartments that pay this fee, and we assume this is the second most expensive school. And finally, when we brush the most expensive school, we see this here are where the people live, and they're all quite close to this school, so we assume this is the school where people live. This is how we tried to match this data, which is not explicitly given. We have no information what's the fee for each particular school. We only have positions of the school. We have positions of people. We know who is paying how much for the school, so we can reason out of this which school is which fee. Of course, we can't be certain, but still, yeah. And finally, my final example, it's not participant-centric data, but business-centric data, where we have these pubs as units, and we can now see how are these pubs. This is number of check-in counts, so how many people visited the pub. This is the data for the 7 days of the week, starting with Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And so here we have more than one curve for one pub, because we have for each pub one curve for each week. So we have many weeks and many pubs and many curves. We can see a clear thing that in Monday to Friday, in the morning, there is not so much visits, and they have evening traffic, which is much higher. And in the weekends, the traffic is more equally distributed along the day. One interesting fact, we also aggregated this data to compute the number of check-ins per day as one single attribute. And then we saw something interesting, that Sunday ends at midnight in our understanding, if this is correct word. But basically, pubs are open longer. So, and if we have some visits after the midnight, they are counted to Monday. But this is wrong. I mean, this is not wrong. Don't get me wrong. This is correct. This is Monday. But in our analysis, we would like to count them as Sunday visits. So we shifted the borders of the days when aggregating the data to be more consistent with our understanding what is a weekend. So weekend does not end on midnight on Sunday. Be aware. Yeah? And maybe, yeah. And so these are small things that you can see in visualization. Maybe you don't think about them when you process the data. You just say, aggregate weekdays, let's go. Sundays, go, go, go. And then you see something is going on. What's wrong with these Mondays? They have these peaks at the beginning, and you say, oh my God, it's Sunday, basically. So, and then, again, you can easily brush them. You can see like very high Sundays, how they are doing on other days. You can see some of them, we could brush this additionally, and then we could see which pub is this. You can get data on the pubs. And for example, here, this pub, we brushed 71 pubs, and you can see which business IDs are these, and how often this does it take. Because we have this count which goes until 65 here, I think, and this is the number of weeks, because that's how many weeks we have. We have weekly data. So, and you can see this business has such a high number of check-ins on Sundays, quite often, more than half of the Sundays in the data set. This has it also very often, and for the other 4, this is more an outlier, such a large traffic on Sunday. Now, of course, we can brush it, we can get individual data for each of them. We can see, okay, we can now brush this business, and we can see exactly on which Sundays does it happen. We can brush this pub, we can see on each Sunday does it happen. I have to apologize here. My plan was to show you this brushing live here, but when I was packing my things, my external hard drive with data set and everything remained on my desk. And, so, but we submitted a video. You can see in the video how we brush and how it moves, and yeah. But this is our main idea. Of course, this is all linked with all views and the map as well. So when you brush one business ID, you can see in the map this one pub brushed, and when you brush any view, you can see all views are brushed. You can configure it with many other views if you want, if you need, whatever you need, it works. Okay, so to conclude, it was really interesting to do with this, and we think that interactive visual analysis helps us in understanding the data. We can, as I try to show you, there's some aspects of what is related with what, how can we map costs to school, for example, and so on. We have this complex data model which helps us. This is what we would argue, and this map is essential for city data. We have spatial data, so we do need a map. It was a little bit work to get this map data into it, but it was so. So, message, money might make the world go around, but does not make the Ohio folks happy. And WASH Challenges is always a great fun. Thanks.
All right, we haven't used this mic today. I'm scared. I'm going to hold it like I've never held a microphone. So.
Just one more remark. We also submitted a poster. I'm not. You said someone said that it's with you in the morning. There are just a few posters, so I hope our was correctly submitted. So and it will be seen there. Okay.
All right. So reminder: if anyone has any questions, please put them into Slido. We've got 2 right now that I will try to go through. So. Let me actually just say first, I love the idea that you are making these assumptions about metrics and like everything you're saying about, we should redefine or make sure that our definition of a weekend, works the way that we think it should work. We should set out an expectation for, what it might mean for a business to be prosperous by looking at the travel distance. So there were a couple questions about that. So. The first says, how did you arrive at the visual hypothesis that more prosperous pubs have a certain kind of shape in that travel histogram that you're plotting? And was that informed by looking at the data a bit first? Or did you say up front, we're going to look for travel distance and then go and verify it in the viz?
The latter was the case. So we first said, let's look at the travel distance. I mean, we were reasoning, let's see what does it mean a pub is popular? So, and then we thought, well, if something is popular, people will come from a greater distance, and then we decided to make these histograms. Still, most of the people come to nearby pubs, but there are a few of them who are willing to travel a larger distance. So this measure of popularity, this is another question. But still, some of them are more popular for sure. But we came to it just reasoning. Let's see the distance. Let's make a histogram of distances, and then we did it. Yeah.
Awesome, thank you. So the second question that we have is a little bit related to that. It says, how do you trade off the benefit of displaying those kinds of histograms directly on the map, which you said, it can be nice to see that right alongside the map data. And what potential concerns might you have about visual clutter, and is there some kind of sweet spot of providing that visual evidence right alongside the map, but not cluttering it too much.
Yes. What we did basically, we had them first offline, I mean off map, not offline, so separately, but then it was hard to match them. So we have these PUBs IDs and so on. And then it might be due to our map, to the city shape, or I don't know what's the right word. There are a lot of white space around the map. This is not so in every city. But in our particular case, we thought, okay, on one hand side, we have this valuable screen space that we are losing because of the city shape. We can't do anything about it. Of course, if we zoom in, we don't lose it, but then we lose the context. And on the other hand, we have need to link the histograms to spatial context, so we just place them. This placement is not automatic, just to be clear. So we can move around with the mouse the histograms. There is connecting line is automatically drawn, of course, but we can move them around. Once we are satisfied, we save the position, it's saved in the project file and so on. But I think if we would have much more, we couldn't do it for every apartment. There would be far too much. So, and if we would clutter some important data, it wouldn't be a good choice. But with manual placement, and in a case like this, it works. And I don't think, if the question was going direction, can we provide some guidelines, some automatism for this? Yes, probably, but it would require quite some work, yeah.
Yeah, difficult to provide those guidelines in a general case.
Exactly.
Especially
yeah.
with data sets that could be so rich and everything.
Yeah.
So that's the last question that we have. And with that, let's thank our speaker again. And that will wrap up Mini Challenge 3, but we'll hand it back to Jordan for a wrap up.
Awesome. I just want to give a huge shout out to our tech crew. This is the first session of the first day of our first time back at Viz with any sort of in-person, and they are managing hybrid like a champ. So thanks to our tech crew. So just to recap what we learned today from the VAST Challenge. So we asked our participants to deal with 15 months of data following over 1,000 people that generated 18 gigs of data. In our first challenge, we asked them to characterize the who's who and the what's what of this fictitious city of Engagement, Ohio. In challenge 2, we asked them to explore the patterns of life. How are people moving about the city? How are they engaging with various businesses? What does it look like as people change jobs and apartments and move in together and separate? And in challenge 3, we asked people to zoom out and explore the sort of economic realities of this city, to make some recommendations about how the city might invest in its future infrastructure to be able to support all of these different mechanisms that go into a city running and sort of community living. If you liked this challenge, if you liked this open-endedness and this sort of meta reasoning that we asked to do as separate from the needle in a haystack, I'll give you a quick teaser about 2023. We'll be thinking about knowledge graphs. So this idea that we connect people and places and things with logical relationships, not necessarily explicit, literally encoded relationships from the data, but actually have to think about, situated in context, what does it mean for these people to engage in these ways with these items? So for our, wow, we're gonna wrap up right on time. I'm super proud of us. So to land on our final farewell, the future is coming and we will see you in Melbourne in 2023. Thanks so much for joining us for the VAST Challenge this year.